So in this video we are going to discuss about thermopiles. Thermopiles are indeed used in wearable devices for various applications. A thermopile is a sensor that generates an electrical voltage in response to a temperature gradient across its surface. This property makes thermopiles useful for measuring temperature difference and thermal energy. In wearable devices, thermopiles can be employed for several purposes. First, temperature measurement. Thermopiles can be used to measure body temperature or ambient temperature. By placing the thermopile sensor in contact with the skin or in the proximity of the environment, it can detect temperature changes and provide accurate reading. Second purpose, heat flux sensing. Thermopiles can be utilized to measure heat flux, which is the rate of heat transfer per unit area. By monitoring heat flux, wearable devices can access thermal comfort or track heat dissipation from the body during physical activity. Third purpose, energy harvesting. In some cases, thermopiles can be used to harvest energy from temperature gradient. Wearable devices equipped with thermopiles can capture waste heat generated by the body and convert it into usable electrical energy to power the device or recharge its battery. Fourth one, contactless gesture control. By using an array of thermopile sensors, wearable devices can detect the heat signature of the user's body or hand movement. This enables contactless gesture control, allowing user to interact with the devices without physically touching it. Fifth point, sleep monitoring. Thermopiles can also be integrated into wearable sleep monitoring devices. By measuring temperature changes on the skin surface, these devices can analyze sleep pattern, detect sleep stages, and provide insight into the user's sleep quality. Overall, Thermopile offers a versatile solution for temperature related applications in wearable devices, providing accurate measurements, energy harvesting capabilities, and potential for innovative interaction method. Good morning to one and all present here. In this video, we are going to discuss about thermopiles. Usually, we don't require large size thermopiles for the maximum power generation in a wearable TEG. The only requirement for a TEG is that it must have a thermally matched thermopile with high thermal resistance per square centimeter of the skin. However, the power per unit area, at least within the 4 to 10 millimeter thickness of a TEG, scales linearly with its thickness. If a small size thermopile is used in such TEG, the distance between two plates of a TEG must be kept the same. The design of a TEG changes a little. That is, one or two thermal shunts must interconnect a small size thermopile with the plates. A thermal shunt is a thermally conducting element such as a spacer, a fin, or a pillar that thermally shunts a part of the environment. Then a miniaturized thermopile can produce about the same power in a TEG of a fixed thickness as obtained by using large size thermopiles purchased on the market. This doesn't mean that any small size thermopile is good for wearable devices. Still, both the electrical contact resistance and thermal conductance parallel to the thermopile in a TEG must be minimized because these are parasitic factor that adversely affects its performance characteristics. The modeling of a thermopile in a wearable TEG shows that due to scaling laws, the smaller the thermopile, the lower aspect ratio is required to provide its thermal matching. What is aspect ratio? An aspect ratio means it is a ratio of the length of thermocouple legs L to their lateral dimensions T. Commercially available thermopiles requires high aspect ratio. For the device model in the figure, it must exceed 20. The figure 2.13, it represents a design of wearable TEG with a small size thermopile. In the figure I have shown 1, 2, 3, right? So what is 1? 1 means it is a thermally connected to the plates. That is thermopile, right? Second one is one is a thermopile that is thermally connected to the plates. Plates is 3, and by using a thermal shunt, the thermal shunt is 2, right? Okay. The figure B, it represents modeled dependence of optical parameter of a thermally matched thermopile in a wearable TEG of 3 cross 3 cross 1.7 centimeter cube size of the length of the thermocouple legs. So what is N? N is a optimal quantity of thermocouples, and L by T is shown. It's a aspect ratio of thermocouple legs, and R suffix TP is the thermal resistance of thermopile, and difference between T and T suffix TP is the temperature difference between the hot and cold junctions, and P is the power calculated at contact resistance of 10 ohm square centimeter and 100 ohm micro square meter between semiconducting legs and metal interconnects. So in the x-axis you have a length of thermocouple legs which is usually in millimeter, and in the y-axis you have a aspect ratio. So let's come to the topic. At length 2 millimeter and 50 at L is equal to 15 millimeter. Okay, and so this both values essentially exceed capabilities of industrial technologies. Therefore, the only practical solution has been found to build the TEGs which will be discussed now. That is namely the use of multi-stage thermopile, and if we decreasing the thermopile size, which causes proportional decreases of aspect ratio that is required for the same thermal resistance. As a result, at a length of thermocouple legs of about 10 micrometer, the optimal aspect ratio decreases to the value acceptable in microelectronic and microelectromechanical systems, MEMS technologies. At larger dimensions, thick film and inkjet printing technology could be used. Instead, in thermopile fabricated on a polymer tape, as well as in membrane based and membrane less thermopiles. With microelectronic technologies, the aspect ratio required for 6 to 15 micrometer long thermocouple can be reached using projection lithography, because a critical dimension of 1 to 3 micrometer is sufficient. One of the possible design, which is shown in the next figure, right? A height of 6 micrometer with inclined thermocouple legs has been already reached in the technological process developed for the polycrystalline silicon germanium. This height corresponds to about 14 micrometer length of thermocouples. A research is ongoing towards practical demonstration of polysilicon germanium thermopiles with high aspect ratio. The required low contact resistance between semiconducting legs and metal interconnects, that is less than 100 ohm micro square meter, seems feasible. Alternatively, an on-chip vacuum packaging can enable required performance characteristics even at larger contact resistance. To obtain performance characteristics as shown in the figure, an SEM picture of polysilicon germanium thermopile test structure with a 6 micrometer topography and a critical dimension of 3 micrometer. Thus, film technology for BITE material still must be developed. Thick film BITE process have already been demonstrated. In the near future, thermoelectric properties of film based BITE are expected to approach those of bulk materials, but this is not an easy technological task. Miniaturizing of thermopiles offers a potential for essential reduction of the fabrication cost. The expected production cost of micro machined thermopiles is by a factor of 100 to 1000 less than the cost of today's thermopile on the market, because only 1 to 2 square millimeter of the wafer is required for a compact wearable TEG. A film based thermopile on a polymer tape could require several square centimeter of the tape, a 100 times larger area. However, the low cost of thin film and inkjet technology and the tape itself could result in a low cost too. Therefore, wearable thermopiles can be very competitive on cost with the batteries in mass production. So far in this unit, we have discussed about wearability issues, technical challenges, power requirements, human body as a heat source for power generation, hybrid thermoelectric photovoltaic energy harvest, and then this topic thermopiles. So from the next class onwards, next video onwards, we are going to discuss about unit 3, that is wireless health system. Some of my reference for making these videos I have given below. First one, Analisa Bonfiglo and Dilo D. Rossi. Wearable monitoring systems, Springer 2011. Second one book is Gong Zong Yang Body Sensor Network, Springer 2006. Third one is Fundamentals of Internet of Things, IoT and Wearable Technology Design, IEEE Plus, Willy Higher Road. Fourth one, Wearable Sensor Fundamentals, Implementations and Applications, edited by Edward Sasunovo, second edition. So thank you for listening to this video. Thank you, Ananda.